All right, we are going to find a power series and its interval of convergence for a function. In this case, it's a rational function, has no asymptotes because squaring a term and adding to it will not give you 0 in the denominator. I put it into the calculator a second ago, and this is what the function looks like. I've zoomed in on it a little bit. You can see it a little bit more clearly there. So we're going to approximate this with a series of terms. In this case, it'll be a geometric series expansion. So let's look at a geometric series just to review, because I think it's important to understand where this all comes from. In this case, n equals 0 to infinity for a geometric series is very simply x to the n, which when we start writing the first few terms will give us 1 plus x squared plus x to the third, and so on. And we know that if x is less than 1, our multiplier that keeps multiplying and multiplying and multiplying will make it smaller and smaller and smaller, and it will converge, and we can get the sum. And the sum has a very simple formula, which is the first term, in this case 1 over 1 minus what that magic multiplier is, the common ratio, or in this case we're using x. All right? So that's the simple formula that will give us what this sum is from 0 to infinity. Okay? So what our goal is to take this expression here for the function and break it down so that it's written in this form, and then whatever x is, that will be the thing that will plug into our power series for x. Okay? So I'm just going to write this, f of x equals, and I need to get a 1 up there, so I'm going to take out the x. I can do this now because later x will be a constant. It'll be our multiplier, so it will not affect this sum as it's not influenced by n, so I can pull it out. So we've got that. Okay, well then I'm going to get the x written second and the 1 written first, so I'm going to write it like this. And then finally I'm going to try to get that minus sign in there, so I write x and then 1 over and then 1 minus, and I write a minus 2x squared. Okay? And now I have got this written in this form where in place of x I've got that minus 2x squared. So that means I can write this with that x out in front as the summation from n equals 0 to infinity of minus 2x squared to the n. Again, I just go up to my geometric series and I replace x with what I found x to be in this form. So use this as a template and go through those steps and you'll be good. But now I'm going to clean this up a little bit and write it in proper form. If I bring this n in as an exponent to each of these, and I guess before I do that I'm going to pull out that negative sign, because we usually write that as negative 1. In this case will be to the n. I'm still going from 0 to infinity. And then when I pull this n in with the 2, I'll get 2 to the n. And then when I multiply the n times x squared, that'll give me x to the 2n. But don't forget the x out there, and when I multiply that in, I'll have 1 more x. In this case, I'm going to put it right in as an exponent. So there it is. There is my power series written in sigma notation. But we're not done. We're going to try to find the interval of convergence. So I need to use the ratio test to do that. And I just very carefully replace n with n plus 1. And I'm going to let that n go to infinity. And I'm going to look at the absolute value of that ratio. So I've got negative 1. In place of n goes n plus 1. I've got 2, and in place of n goes n plus 1. I've got x to the 2 times n, so in place of the n I do n plus 1, and then that plus 1 is out the side there. That's all over negative 1 to the n, 2 to the n, x to the 2n plus 1, and I just have to carefully go through and do my cancellation. Well, these guys will always be alternates, so that's going to be just a negative sign. Always, and I've got 1 more 2 up above, so let's see, I will have more x's up above, so I don't need a fraction bar, so I'm just going to write the 2 like that. And notice the n is gone, it's just the number 2. And when I distribute that 2n, I'm going to get 2n plus 2 plus 1. I'm going to make that into a 3. So 2n plus 1 and 2n plus 3. I know that my x to the 2n's will cancel. And I've got x to the 3 over x. That gives me x squared. And the limit, as n goes to infinity, there are no n's in there. So this just gives me the absolute value of negative 2x squared. And that's going to give me my radius of convergence that I know will be less than 1. The ratio test will tell you that something will converge when that is less than 1. So when does this happen? Well, I can divide by 2, and then I want this, when I square it, to be less than 1. So that means it's going to be divide by 2, take the square root. It's going to be square root of 1/2 will be negative radical 2 over 2, and x, and positive radical 2 over 2. So in interval notation, we would write that as minus radical 2 over 2, comma radical 2 over 2. It's geometric, so you can never be equal to 1. It's got to be less than, so I can do that. There are times when you need to plug in the endpoints and check. You can certainly do that. If you plug in negative radical 2 over 2 and are very careful with all the exponents, you'll see that it will diverge. All right? So I think it's kind of cool to write the first few terms of this. So if we go back here and say, all right, our geometric series, when I plug in 0, that gives me 1, it gives me 1, that drops out, it gives me x. So my power series approximation is going to be x. And then when I plug in 1, I'll get a negative 2, and then I plug in a 1, x to the third, minus 2x to the third. When I plug in a 2, I'll get positive 4x to the fifth. And then you see the pattern, I think. When I plug in a 3, I'll get a negative 8x to the seventh, and so on, plus 16x to the ninth. All right? So if I go back to the calculator and type those in, I did, and now I can turn on the equal sign, and we can look at this, and there's our original function, and here's our approximation. And you can see that it does a really good job over that interval. All right, I set the interval to be plus and minus radical 2 over 2. All right, we can get a little bit closer if we add one more term. So if I go down here and go out to the end, or I could have inserted at the beginning, but just so you see that I typed it all in. What are we up to? We're up to plus 16x to the ninth. And if I graph that, it should be a little bit improved. And with successive terms, we would get closer and closer and closer and closer, but only over the interval, right? It would just pull this up, but it's never going to complete it out here. It's always going to stop at that interval of convergence and then deviate from there. All right, hope that was helpful.